Hi, my name is Bob Cheesebrough, and I'm a technical consulting engineer in Intel's compiler team. Welcome to the third in a series of videos covering Intel compiler vectorization essentials. In this video, we explore explicit vector programming at a high level. There are many ways to vectorize. Some methods are easy to use with little programmer control, while other methods may provide inherent programmer control but suffer from poor portability and difficult and expensive code maintenance. Many of you should be familiar with the compiler's ability to auto-vectorize by now. Auto-vectorization, from the programmer's perspective, can be a freebie, gaining performance with nothing more than a compiler switch. Some of you may be accomplished at using assembly language, or perhaps using SIMD vector intrinsics to explicitly vectorize an application. Somewhere in between lies explicit vector programming. This talk will focus on that. The trouble with auto-vectorization, as we have stated, even though it is easy for a developer to use, is that the compiler is limited in what it can do for you automatically due to the serial limitations of the underlying language, meaning that many loops will not be vectorized, and even the ones that get vectorized may not be vectorized efficiently due to conservative assumptions that the compiler is forced to make about the code. The trouble with assembly language, or vector intrinsics, is that they become platform specific. They're not portable, say, between Intel Xeon processors and Intel Xeon Phi coprocessor platforms, for example. We are focusing on extensions to languages that have standard support and work across Intel platforms, from graphics processors to CPUs to coprocessors. This slide draws the analogy between explicit vector programming and OpenMP thread-based parallelism. At the highest ease of use level, a developer could opt to use auto-parallelization by invoking a compiler switch to parallelize whatever loops the compiler deemed safe. Similarly, a developer could simply compile with a compiler auto-vectorization switch, or in the case of the Intel compiler, this could happen by default at O2. The compiler would seek to auto-vectorize whatever loops it deemed safe and profitable to vectorize. If a programmer wanted more control using thread-based parallelism, she may opt to use Windows threads or POSIX threads to get complete control over the parallelization process. The trade-off is that portability is lost once either Windows or POSIX threading model is chosen. Similarly, the same developer might wish to gain ultimate vectorization control using compiler intrinsics, but this choice also comes at the expense of portability, as we mentioned previously, in that intrinsics developed for the Intel Xeon processor platforms in many cases are not supported by the Intel Xeon Phi coprocessor platform, and vice versa. Similarly, explicit vector programming using OpenMP 4.0 vector extensions gives the developer sufficient programmer control in many cases and still provides platform portability. The aim here is to provide a programming model that provides both thread-level parallelism and SIMD-level parallelism to existing languages while still providing a high degree of portability. Now note, developers should note that while vector and parallel codes may port between platforms such as Intel Xeon processor and the Intel Xeon Phi coprocessor, it is still advisable to tune the application carefully for each platform. There could be different memory bandwidth, cache locality, data alignment, and vector length sensitivities, among others, that impact performance on any given platform, and each application will have different sensitivities to these issues. Now we will explore a very high-level simplification of how the vectorizer works in the Intel compilers and how developers interact with the compiler to get your code to vectorize. A programmer develops or modifies high-level scalar code on the left, then describes the vector parallelism in the high-level language construct. This includes the original code on the left, plus the modifications such as OpenMP 4.0 SIMD-enabled functions and pragma-OMP SIMD. The vectorizer, which is a component of the compiler, not a human programmer, maps vector parallelism onto the appropriate target vector instruction set architecture. A major part of the vectorizer is common to all vector instruction set architectures. This is how the write once and retarget mechanism works. After targeting the instruction set architecture, the compiler will work to do other optimizations and do the code generation step. The focus of this video series is the yellow boxes consisting of the OpenMP 4.0 SIMD-enabled functions and the pragma-OMP SIMD in the lower middle portion of the screen. The vectorizer makes retargeting easy. At the simplest extreme, a single compiler switch could retarget for a different architecture. Of course, for best performance on any given architecture, specific tuning for the platform data alignment, cache size, and other platform details and sensitivities would be needed. Let's look at the serial code on the left. For each loop iteration, a single value of the B array is read and added to a single value of the C array, and the sum is assigned to the corresponding array element A. The loop then repeats. Notice that a single floating point addition is done per loop iteration. Let's look at the vectorized code with the OpenMP SIMD pragma in the lower left. Notice that a simple OMP SIMD pragma is annotated just prior to the declaration of the loop. It signifies that the developer is taking explicit control over the vectorization behavior of the loop. In this simple form, without any modifying clauses, it compels vectorization even if the standard efficiency heuristics in the compilers say no. It ignores language constraints that hinder vectorization. By using this directive, the developer is asserting that the arrays have no data dependencies on each other and that the loop bounds are not changing. The vectorized behavior of the loop is different from the scalar version. We will assume that the vector length in this example is 8. So in this case, only n divided by 8 loop iterations are performed thanks to our vector length. The loop is chunked out into iterations of size 8 iterations each. In each iteration, 8 times more floating point operations are performed. So elements 0 through 7 of the B and C arrays are read in 8 vector lanes. They are summed, and the results are written 8 at a time to elements 0 through 7 of array A. This results in a speedup, for this example, of 8x. The advantage of this approach is that it is suitable for keeping the original loop form to minimize the amount of change. This concludes our third video. Please take a few minutes to watch our next video in the series, Performance Essentials 4, where we begin our exploration of OMP SIMD.